Welcome one and all to the official final review for Econ 378. I'm here at my apartment filming from this janky couch with a janky whiteboard because the librarians at the library didn't like that I was using a study room without a study group. So we are here on my couch in my apartment with this janky whiteboard. Hopefully it will be visible to everybody. But this video, I'm hoping, won't be super long. We're going to quickly review some of the different cases for hypothesis tests, as well as confidence intervals. And then we're going to talk a little bit about bias and estimators, as well as matrices for a little bit. I'm not going to be going over the practice questions at all. Those are posted on the Learning Suite and have answers posted as well. With reasons for the true and false, and also a little bit of step-by-step for the too long answer questions. So the first thing to note is that most of the test is going to be based around hypothesis tests and confidence intervals. And it's important to recognize that both of those are relevant pieces of analysis, but that they're two different ideas. That we don't derive hypothesis tests from confidence intervals, nor vice versa. We can't really read anything from one to influence the other. Rather, they're two different forms of analysis. So our most basic kind of setup for a confidence interval is going to be a confidence interval regarding one mean. So the way we set this up is we have X bar, which is our sample mean, minus the true mean of the populace over the square root of the variance over the sample size. This number, when we solve for it, when we plug in our sample mean as well as our variance and our sample size, this is going to yield for us a margin of error for our confidence interval. So essentially the idea is that we solve this in order to get mu by itself, the true population mean. And by the time we solve this out, we end up with, here, one second. Where did my eraser go? Here we go. Just going to write it down here because I think it'll be easier to see. Our final confidence interval is going to be our sample mean plus or minus some z/t score times the square root of our variance over our sample size. And this is going to give us an interval. This t or z score is determined by the size of the interval or the confidence of the interval that we want. So if we want a 90% confidence interval or a 95% confidence interval or a 99% confidence interval, these scores will change. And as we increase our confidence, we also have to increase the size of the interval. Because in order to be, more confident that the true population mean lies within that interval, we need a larger interval. So this is kind of the basics of a confidence interval. We have X bar, we have our standard deviation, and we have our sample size, but we don't have a mu. It should be noted quickly right here that the difference between a z-score and a t-score is determined, whether we use one or the other, is determined by whether or not we have the true variance of the population. If we only have a sample variance or a sample standard deviation, we'll use the t table, a t-score. If we have the population standard deviation or the population variance, we will use the z-score, the z-table. We can also use a z-score if our sample size is sufficiently large. So even if you don't have the true population standard deviation. If your sample size is large enough, higher than 30, then we can use a z-score and not a t-score. Now, when we switch to doing a hypothesis test, this formula is going to stay the same. We're still going to be using this formula, except for now we are assuming some value for the true population mean. So previously, we were solving to find a confidence interval within which we were some level of confidence that the true mean fell within that interval. Now we're not solving for an interval, rather we're solving to find the probability of us observing this sample mean given some population mean. And so whenever we do a hypothesis test, we're going to start with an assumption about what the true mean of the population is, which is going to be our null hypothesis. So our null hypothesis could say something like mu equals 5. And now we can plug in all of our values that we have for our sample mean, for our sample standard deviation, and for our sample size, as well as this null hypothesis value for mu, in order to find a test statistic. So let's just say, for the sake of this example, that x bar equals 7, that our sigma squared equaled, that sigma squared equaled 10, n equals 30. So if we do all that, we find 7 minus 5 over the square root of 10 over 30, which is just 1/3. So I'll put 1/3 down here. So we would plug in all that and we would do the math and we would find some test statistic. In this case, I don't have my calculator on me, but this will be 2 over the square root of 1/3. This is going to be a pretty high test statistic. But what we now do is we take that test statistic and we compare it to some critical value. Now, our critical value is some value on the t-table or the z-table, so some z-score / t-score that corresponds to a certain probability. You'll find your critical value by knowing what the alpha is, or the level of significance. Typically, you'll see an alpha of 0.1, 0.05, or 0.01. What the alpha is saying is, okay, if we observe some test statistic that has a lower probability of occurring than the level of significance, then we will reject the null hypothesis. So all of these probabilities, 0.1, 0.05, and 0.01, have corresponding scores on the z-table that we can go to. And so what you'll do is you'll take your level of significance, you'll go to the z-table, and you'll find the corresponding critical value that corresponds to 5% above, lies above that critical value. So to visualize things a little bit, let's say that you have the null hypothesis that mu equals 5, and your alternative hypothesis is that mu is greater than 5. You find some test statistic that lies up there, And then for the given alpha level, in this case, let's say 0.1, you find the value on the z-table where only 0.1%, only 0.1 or 10% of all values lie above that point. And then you'll simply compare either the p-value of your test statistic, the p-value being the probability of it falling above your test statistic. You can either compare your p-value to your alpha level, or you can compare your test statistic to the critical value. And we're going to reject the null hypothesis if our test statistic or our p-value are more extreme than the level of significance or the critical value. By more extreme, I specify more extreme because if we were doing a two-sided test or a test on this bottom part of the curve, we would be looking for a test statistic that was smaller than the critical value. Whereas here on the upper end of the tail, we're looking for a test statistic that's greater than the critical value, right? So it's not necessary to show that both your p-value and your test statistic are more extreme. It's sufficient to just show that one or the other is more extreme than the critical value and the level of significance. You just have to prove one or the other, though sometimes you're asked to report the p-value specifically. Okay, so on the topic of hypothesis tests, our null hypothesis sets what mu is, and that will then directly impact what our test statistic is. The purpose of the alternative hypothesis is to direct kind of the focus of our test. So if say our null hypothesis was that mu equals 5, if our alternative hypothesis was that mu was less than 5, that indicates to us that we're doing a one-sided test, and that our one-sided test will be focused on the bottom end of the distribution. So we're looking for the likelihood that mu is less than 5. If our null or our alternative hypothesis is that mu is greater than 5, that means that we're doing again a one-sided test, but that we're focusing on the upper tail of the distribution. If our alternative hypothesis is simply that mu is not equal to 5, this means that we're doing a two-tailed test. So we're going to be looking at the top and the bottom of the distribution, because the alternative hypothesis could be accepted if mu was greater than 5 or less than 5. So we're going to be looking at both ends. Now, an important note here is that our level of significance we're going to treat slightly differently depending on whether we're doing a one or a two-tail test. So let's say we have an alpha of 0.1. If we're doing a one-tail test where mu is greater than 5, we would look to the upper tail and our alpha level would be 0.1. So we would be looking for the critical value above which 10% of the values lie. However, if we're doing a two-tail test with a level of significance of 0.1, now we need to divide that level of significance in two. So instead of looking for where 10% of values lie below and 10% of values lie above, like we were doing before with a one-tail test, we're going to be looking where 0.05 values lie below and 0.05 values lie above. We need to split that level of significance in two because we're looking at both ends of the distribution. All right. So now a brief overview of the types of tests that we do. So I just modeled a little bit of what we can do with a single mean. We also have hypothesis tests for proportions, which you'll see if you're working with a Bernoulli distribution, and that looks very similar. We do p hat, which is essentially x bar. It's the proportion of our sample minus the true population proportion over the square root of the variance. And if you recall, the variance of a proportion is just the proportion multiplied by 1 minus that proportion over the sample size. So very similar to means. We're just switching out for proportions. Some notes with proportions. If you are doing a confidence interval with proportions, this is what you're going to do. You're going to have p hat minus p over the square root of p hat times 1 minus p hat over n. We're going to be using p hat for all of these because we don't know what the true population proportion is, and we don't have a guess or an assumption about what it is. So the only proportion we can plug in down here for these proportions is p hat. However, once we switch to doing a hypothesis test with proportions, now, because of the null hypothesis, we have an assumption for what the true population proportion is, right? Because of that, we're going to plug in what our assumption for the proportion is into these bottom parts into the denominator as well. So up here we have p hat, and p hat. Down here we have p, and p. So we don't use p hat in the denominator for a hypothesis test because we have an assumption about what the true population proportion is. Okay. So now with proportions, the one other complicated part about proportions is dealing with differences in proportions. A hypothesis test of a difference in proportions. Here, we're going to have p hat 1 minus p hat 2 minus p1 minus p2 all over the square root of p hat 1 times 1 minus p hat 1 over the first sample size plus p hat 2 times 1 minus p hat 2 over the second the second sample size. Now, our procedure on what proportions we use will change slightly based off of what our null hypothesis is. If our null hypothesis is that these proportions are the same, that p1 minus p2 equals 0, or that they're the same, in that instance, when we run the hypothesis test, we will replace all of these p's in the denominator with a new proportion called p pooled. P pooled is found by simply adding up, well, really by finding an average of the two proportions. So you're going to add up the sample sizes to create a new kind of master sample size. And then you're going to add up kind of the proportions on the numerator. Not really the proportions, you're going to add up the number of, the number of positive responses, the number of ones, essentially. So if your two samples, proportion 1 was 30 out of 50, and proportion 2 was 60 out of 70, you would do 30 plus 60 over 70 over 50. So you're creating a combined proportion for both of the populaces. This p-pooled will then replace all of these proportions in the denominator. And the reason why we're doing this is that our assumption, our null hypothesis, is that those two proportions should be the same. And so we're finding the likelihood of the difference that we observe existing if they have, the same proportion. However, if our null hypothesis is that one proportion is bigger than the other, say if it's proportion 1 minus proportion 2 equals 0.05, this means that we're assuming that they're not the same size, that P1 is larger than P2. And because of that, we can't create some master pooled proportion, nor any assumption about what those proportions actually are, because P1 and P2 could presumably be any proportion so long as P1 was larger by 0.05, right? And so now when we run this, we just have to use P hats, the P hats in the denominators, because we don't have any assumption about what the true proportions for the populaces are. We have to just use our sample proportions. So some nuances there with differences in proportions. Lastly, let's talk about chi-squared briefly. So chi-squared is a little bit odd. It's the distribution itself is different from the t-table or the t-distribution and the z-distribution. The z-distribution or the normal distribution is the classic bell curve. And then the t-distribution looks very similar, just with fatter tails. And the larger your sample size is, the more the t-distribution looks like the normal distribution. Chi-squared, on the other hand, is kind of offset. Actually, that's not a great drawing. It's kind of lumped up towards the front, and then it tails off slowly. And the chi-squared table gives us a set of values, and it specifically gives us the proportion of values that lie above the coefficients selected. So typically for like the normal table gives us everything below our selected value. The chi-squared table gives us the opposite. It gives us everything above our selected value. We use chi-squared when we're trying to work with standard deviations. And so if you're trying to find a confidence interval for a true standard deviation, true population standard deviation, or if you're doing a hypothesis test based around standard deviations instead of means, you're going to use chi-squared instead of the normal distribution or the t-distribution. Now, I'm going to take a bit of a knee here. So the formula that we use is n-1 times s squared being our sample variance, over sigma squared, which is the true variance of the data or of the population. So if we're finding a confidence interval with this, what we need to do is we need to get sigma squared by itself. We know that this is going to lie between some values on the chi-squared table. So in order to get sigma by itself, we can divide these chi-squared values by n-1 and s squared. But then Sigma squared is now by itself, except for its inverse. It's 1 over sigma squared. So if we want to get sigma squared truly by itself and not the inverse of it, we have to take the inverse of this whole function. So what we're going to end up with is we're going to have to flip these inequality signs because we're taking the inverse. The n minus 1 s squared will end up on top with chi on the bottom for both of these. So this will be kind of the formula that you use to find a confidence interval for the standard deviation. And these chi-squared values that you choose will correspond with the level of confidence that you're looking for. So if you're looking for a 95% confidence interval, that means that you need 2.5% of the values to lie above your interval and 2.5% to lie below your variable. So back up here at the beginning, you would find the chi-squared value for 0.025 on the bottom. On the bottom, you would have the chi-squared value for 0.975. Since chi-squared, as I said before, gives us all of the probability of the values above our coefficient, if we want to find what chi-squared value delineates the bottom 2.5%, we have to find the place where 97.5% of values lie above. So that will be our bottom limit at first, and we'll have 0.025 up here. So this is the value, the chi-squared value, above which 0.025 of the values lie above. Now, when we do all this fancy math in here to get sigma squared on its own, you'll notice that the chi-squared value above which 97.5% of values lie, that this is going to be a comparatively smaller number than the chi-squared value above which 2.5% of values lie above. And that makes sense, right? Because if we have a smaller number in the denominator here, that means this whole value will be larger than this whole value, which is exactly what we want, right? Because sigma squared is larger than this value, but smaller than that one. And so there's some wacky switching of inequality signs that can kind of throw you for a loop. And it can be a little bit hard to think about this, but just study the chi-squared table, look over it, and learn how to read it well. And this becomes fairly intuitive once you can see how it's giving you the data. Some other notes real quickly on distributions. Degrees of freedom for t-tables for the t distribution is just n minus 1. So your sample size minus 1. Degrees of freedom for the chi-squared table can be found as half of the variance of your function, or as the mean of your data. Alrighty, I think that covers it for distributions, at least for now. Real quickly, let's talk a little bit about matrices. So, matrices are essentially tables of values, tables of data that we can observe. There are a couple properties that are important to know. So first off, we have transposing. Transposing switches the rows and columns of a matrix. So let's say that matrix A is 2, 1, 0, 3, 2, 5. A transposed means that this column is going to become the first row. So we get 2, 1, 0. And that this second column becomes the second row, 3, 2, 5. So that is transposing. If we take the inverse of a matrix, we don't actually need, for the purpose of this class, we don't need to calculate what any of these inverse matrices are. But the important thing to know is that the inverse of a matrix times the matrix is equal to the identity matrix, which is a matrix filled with ones and zeros. Now, the identity matrix is important to know about because in matrix algebra, it functions essentially as a 1. If you multiply something by the identity matrix, it just equals the thing that you multiplied by. There we go. Now, some important terms. Non-singular means that you can take the inverse of the matrix. So if a matrix is non-singular, it means that you can take an inverse of it. If the matrix is singular, it means you can't take the inverse of it. Another important term is that a matrix is symmetric. And what that means is that A and A transposed are the same thing. So that can be useful for matrix algebra, knowing that you can take the transpose of it and it ends up being the same thing. In terms of doing some math with matrices, adding matrix is very easy. Adding and subtracting is very easy. You need to have matrix with the same dimensions. And if you have matrix with the same dimensions, then you can add them straight across. So the first value, the first column and first row, is equal to the first column, first row, plus first column, first row. So 2 plus 6. Same for the next one, 3 plus 9. Then down here, 7 plus 4. And then over here, 8 plus 5. Pretty easy. Multiplying matrices is slightly more complicated. What we need in order to multiply matrices this first matrices that I've written here is 3 rows by 2 columns. Now over here, I've created a 2 by 2 matrix. In order to multiply matrices, these two inner numbers have to be the same. So since they're both 2, I can multiply this matrix. And the resulting matrix will have the dimensions of the outside numbers. So 3 and 2. My resulting matrix will be a 3 by 2 matrix. And then the way you multiply is you do first row, everything in the first row times everything in the first column. And that first row, first column is going to give you the first value in the matrix. This first corner. Then to find this top corner, you would do the first row times the second column. For this next line, second row times first column, second row times second column. Last row, third row times first column, third row times second column. Like that. Matrix calculus is pretty simple. If you say have x1, x2 squared plus x3. If you have a function like this, what you're going to do is take the partial derivative of this function with respect to all variables within it, and that's going to result in a in a matrix of values. So if I take the partial derivative of this with respect to x1 will drop out and x3 will drop out, and we'll end up with just x2 squared. If I take the derivative of this with respect to x2, then we'll end up with 2x1, x2, and the x3 will drop out. And then once I take the derivative of this with respect to x3, we'll just get 1. So we receive this matrix, and then you'll also be given some sort of matrix of the values of x1, 2, and 3. So you could be given a value sheet of like 5, 10, 3. And then to evaluate this matrix, we would simply plug in values where needed. So this first square is x2 squared. So we would look at what x2 is. It's 5 and square it to get 25. This next row, we've got 2 times x1, which is 10, so 20, multiplied by x2, which is 5. So that's 20 times 5, or 100. And then lastly, we have no variables in this last column, or this last row, and so we just have 1. Pretty simple. Okay, let's see, we've gone over matrices. We've gone over various distributions. We've gone over confidence intervals and hypothesis tests. The one other thing I wanted to briefly touch upon is bias and efficiency and consistency. So bias, all of these terms have to do with estimators. So an estimator is some sort of formula that we use in order to estimate a population parameter using data that we receive from our sample. The bias of an estimator is simply how far away it is from the actual population value. So we calculate the bias of any estimator, which I'll write as theta. I know that using these letters can seem confusing and abstract, but just think of theta as any estimator that we could create. The bias of this is the expected value of the estimator, theta, minus the thing I'm trying to estimate. So in this case, we'll call it theta here. These should be theta hats. So one famous estimator is x bar. So if we wanted to find the bias of x bar, we'd find the expected value of x bar minus the thing that it's trying to estimate, which is mu. All right. So these questions can often seem kind of abstract if it gives you some random estimator and it asks you to find the bias of it. But I hope that you guys can realize that finding the expected value of something is something that we've done a lot in this class. And so whether they give you a complicated function or some sort of joint density table or something like that, recognize that the whole first 2/3 of this class was essentially us finding different ways to find the expected value of something. And so I would just study the rules of algebra with expected values, as well as how to find an expected value from a PDF and from other sources. And if you know how to do all of those things, if you can do algebra with expected values and you can find an expected value from a variety of, of functions, then you'll be totally fine on any question that might ask about this. The important thing to remember is expected value of the estimator minus the thing that you're trying to estimate. So if you're trying to estimate sigma squared, don't subtract mu from it. Subtract sigma squared. If you're trying to find the true population proportion, don't subtract mu, subtract the proportion. And something is unbiased if the bias equals 0. X bar happens to be unbiased. The expected value of x bar is just mu. So mu minus mu is 0. The efficiency of an estimator looks at the variance of the estimator. And an estimator can't be efficient per se. It can only be more efficient than something else. So efficiency is always a measure, a comparative measure. We'll compare two estimators and see which one is more efficient than the other. Consistency is the idea that as n goes to infinity, bias goes to 0 and the variance goes to 0. So what this is saying is that as you increase your sample size, your estimator becomes increasingly consistent in the values that it gives you. The example I gave the other day in the review is if I am at an archery range and I'm shooting a bunch of arrows into a target, consistency would be my ability to hit the same spot on the target repeatedly. You can be consistent, though, without being accurate. I could repeatedly hit the bottom left part of the target. I could consistently hit that point, and I would be consistent, but I wouldn't be accurate because I would be missing the middle of the target. Therefore, something can be both biased and consistent. Something can also be unbiased, but not consistent if the variance is very high and doesn't go to 0 as the sample size gets larger. If you have other questions or are worried about questions of bias, many people in the review were worried about questions of bias. I would just go in and do the extra problems related to bias. Many of those are more difficult than questions that you would see on the exam. So if you're able to understand those and do them well, then you'll be just fine. So I point you to those extra problems, which you can find on whatever homework we did about estimators. If you go to the additional problems on that homework, you'll find some examples of things to work on. With that closes off this review. I hope it was helpful in some way. Like I said, the practice problems that I posted are on the Learning Suite along with the solutions. Hunter was also kind enough to send out a practice exam that he received, which I've now emailed out to everybody, so you can also look at that practice exam, as well as working on the additional problems. You guys are going to kill it. I'm proud of you guys. You guys are great and diligent, and I'm excited to see how you guys do.